Hi, everyone. Thank you for watching. My name is Nick Lingler. I'm a leader in Deloitte's Life Sciences R&D practice. And today, my colleague Bill Baker and I will be presenting about Deloitte's approach to using artificial intelligence to drive automation for clinical data from protocol creation to submission.
Hey, and I'm Bill Baker, a specialist leader at Deloitte Science Practice. I've been working in and with pharma biotech companies since the 90s, including creating and running my own CRO, specializing in biometric services for 11 years.
Thanks, Bill. And before we dive into things, I want to establish our objectives for this presentation. I'll start by briefly discussing challenges we face with the traditional approaches to managing clinical study data. From there, we'll spend a little bit of time to illustrate how artificial intelligence and machine learning within an end-to-end system can bring about more efficient clinical trials. Bill will then take us through 3 use cases that demonstrate opportunities to improve upon the current clinical trial lifecycle, and we'll close by providing a summary of the potential benefits of using metadata-driven artificial intelligence and machine learning to automate data flow throughout a clinical trial. So let's start us off by first setting the stage a little. I'll start where we currently see challenges in managing clinical trial data. Over the years, very different groups have improved their internal processes by implementing point solutions. For example, moving from paper CRFs to an EDC. While these solutions are important for that specific group, they did little to improve the sharing of data with other groups. Continuing with that example of moving to the EDC, that was very helpful for data management, but it doesn't automatically tie to the protocol. So by having these disconnected systems that requires each group to manually re-enter the needed information into their solution, that opens the door for inaccuracies and causing unnecessary rework. All this re-entry also prevents any one solution from being the single source of truth. It also causes the need for information reconciliation between those multiple systems, which is 100% non-value added work. Again, you may have templates for your statistical analysis plan, or you may be using structured content authoring, but neither of these examples help the data manager or programmer. Even with the standardization of data components across trials, you still have the time delays caused by the need to manually copy, duplicate configuration information in each point solution. Basically, everything is optimized today in silos for a given process or function. Even as a function may have standardized things, there's no way to automatically bring historical information from previous protocols, what has been previously done. We're relying on people with knowledge and prior experience to bring in this intelligence. These current challenges make it unnecessarily harder as trials become more innovative, as we think about new modalities that get more complex, as we're measuring more and more things in studies, and also as we're incorporating new and additional data sources. So first, how does artificial intelligence and machine learning bring about more efficient clinical trials? And if I look into my crystal ball, what does the future look like? So in recent years, the industry has made significant investment in digitizing processes, basically moving to better workflows and moving to the cloud. However, we still have a number of challenges that exist today. Clinical trials continue to be the most significant component of the time to get a drug to market. And of course, the cost keeps increasing. And although not all, a large portion of the cost and inefficiency in clinical trials can be attributed to manual processes, poorly connected systems, and the flow of clinical data from start to finish. So our goal is to automate data management across the clinical trial lifecycle. We're doing this by creating structured, standardized, and digital data elements from many different input documents and sources, all of which are intelligently interpreted and transformed to set up downstream systems, auto-populate required reports and analyses, and generate content for key clinical trial artifacts. As data moves through the life cycle from protocol to CRFs, to programming, and then to reporting, each step of the process has disparate tools that don't have common metadata-driven capabilities. Again, this means there's no single source of truth. It also means there's a lot of manual, effort-intensive processes to move the data from that start to finish. To complicate things even further, as a protocol goes through amendments throughout the life cycle of a study, which is inevitable, it leads to significant rework and longer cycle times. All of you know this. Today, when there's a change in the protocol, even sometimes a small, simple one, the entire impact analysis and then the modification of systems, data mappings, tool updates, all of this is done by people, and it's incredibly time-consuming. The future, however, it's a much more streamlined, fully connected and integrated data from start to finish. And that's what we're showing on the right-hand side of the slide here. There's full traceability from start to finish. So if protocols go through a change, well, I shouldn't say if they go through a change, but rather I should be saying when protocols go through changes, it becomes easy to identify the impacts of these changes. Additionally, with the power of artificial intelligence and automation, incorporating these changes to the protocol into the data lifecycle can also be streamlined. So there's a lot of untapped potential in this space, and we'll get deeper into these ideas. So to realize these opportunities, let's take a look at the capabilities the clinical organization will have to invest in. Starting on the left here with the protocol builder, modern technologies along with advancements in standards can be used to enable the creation of a digitized protocol. You combine with that the use of artificial intelligence and machine learning technologies, we can help provide smart recommendations and automation based on data from past studies. You combine that with the biomedical concepts being developed as part of CDISC standards, which we know that the CDISC version is expected to be released around the end of the year, but any set of standards can be defined as biomedical concepts. So there's really no need to wait for that. So we combine that with the common protocol template that's been developed by Transcelerate, and that allows us to streamline the creation of a fully digitized protocol. In plain terms, a digitized protocol lays the foundation and provides the necessary metadata for automation to occur and data to flow throughout the clinical trial lifecycle. From the protocol builder, data flows down and automates other platforms. The CRF builder has all of the metadata it needs once a study is built in the study builder. That metadata can then be configured for import into an EDC system, whether that's in ODM XML format or a more platform-specific format such as ALS. An import file can be automatically generated.
And, you know, I think the ability to do this is huge. The time spent by data management and programmers interpreting the protocol and the schedule activity would be eliminated.
Yeah, I mean, totally, Bill, I couldn't agree more. And not only are you eliminating that time, but also you're eliminating that human interaction. And anytime you have the human interaction, there's potential for errors or inconsistencies. So you're enhancing the quality at the same time. So continuing down through the flow, from there, the data flows into the statistical analysis plan creation, where the protocol elements can be automatically included based on templated sections. Additionally, there can be collaborative authoring of the statistical analysis plan, and throughout, there is metadata traceability back to the study builder. This enables automated update triggers to review workflows. So continuing on, next, data can flow into STM Conversion, where data quality checks and source to target mappings can be automated. We'll get to some more details on this a little bit later in the presentation. For now, I'm going to jump on over to the tables, listings, and figures, which can also be created using digitized protocol and elements from the statistical analysis plan. This is all linked to standards. automation of TLFs is enabled by recommendation engines and graph database to manage semantic relationships between the protocol elements, study definitions, and data standards. Based on all that metadata and the advanced artificial intelligence and machine learning analysis, TLFs can be automated. But the value doesn't stop there, because you additionally have the insights that can be identified by these algorithms with no additional effort from the user. Following from the TLF creation, a draft of the clinical study report can be automatically generated, similar to the way the statistical analysis plan is generated.
Yeah, and just like Translate's protocol template, they have templates for the SAP and the CSR as well. And then there, of course, there's the industry standards defined in the 90s by the ICH.
Yeah, thank you, Bill. And to further illustrate how the metadata flows through each of these milestones in the clinical trial lifecycle, let's take a look at the gray boxes on the screen to show a real example. So in this particular example, say you're writing a protocol for a hypertension study. You'll need an endpoint related to vital signs specifically for measuring blood pressure. Based on biomedical concepts and the structure of the underlying metadata in an end-to-end system, that endpoint can be automatically suggested. And once it's added to the study in the protocol builder, metadata about that endpoint can then flow down to other milestones in the cycle. So to expand on this, let's follow the metadata down this cycle. Because the system knows that you need vital signs, it will automatically include the correct vital sign forms in the casebook. So that necessary data will then be collected. It can also annotate those CRFs and create a mapping to the STM vital signs domain. And since it's a hypertension study, and the system knows you'll be doing analysis on the vital signs, it'll know we need the vital signs atom domain called ADVS. So using a related analysis concept, it'll also make recommendations for the type of evaluations and suggest some tables, listings, and figures that you may want to use. And then finally, our vital signs metadata will also help make suggestions for vital signs summaries that should be included in your clinical study report. I want to reemphasize that all of this automation is made possible by two main things: machine learning and the developing advancements in clinical data standards such as biomedical and analysis concepts. Now I'm going to pass it off to Bill, and hopefully if you're not convinced yet, after he focuses on these three main use cases, you will be.
Thanks. As Nick mentioned, I'll be providing an overview of how a few of the steps could be completed. The first step we'll explore is the creation of the protocol and the schedule of activities. The protocol builder module should utilize metadata-driven AI and ML to define the key information that's needed for this study. It will be used to create the protocol document, and then we'll follow with the common protocol template as well as reused in later modules. The next step, we will review the information's lifecycle to define the EDC's visits, forms, and fields needed to support the protocol. We will present a few key tasks that should be supported in relation to the CRF. And the last step we'll touch upon today is the STM conversion, where the study design data will be used once again to create CDISC submission formatted data and the associated documentation that's needed for the NDA submission. Okay, let's dig into some details. The two main efficiency gains are provided by capturing the common study design details as early in the process as possible, and the use of the biomedical and analysis concept metadata link, the study data from protocol all the way through to the CSR. With that in mind, the main goal of the protocol builder should be to capture the study design details with the assistance of the metadata-driven AI and ML. The collection of every piece of that data should be optimized to assist the user with automation by using the AI and ML and standard industry libraries like CDISC and SNOMED, for example. As users begin making selections, the application should be hard at work behind the scenes, deciding which choices to recommend for the next piece of information, and each selection building upon the ones before it. The protocol builder should use AI and ML to create the choices for items like titles, objectives, and endpoints. For example, recommending titles that have efficacy for a phase 3 study, but not for a phase 1 study. Or maybe a better example would be suggesting objectives and endpoints related to resist measurements if the protocol is for a solid tumor indication.
Yeah, Bill, another example that comes to mind for me is suggesting inclusion and exclusion criteria. The system can recommend criteria based on the type of study and what has been used in similar studies.
Oh yeah, good point. Thanks. As with any application that utilizes machine learning, any choices and subsequent modifications should be used to train the model for future studies. When you use machine learning to suggest endpoints and then to suggest the appropriate biomedical concepts, you'll be able to utilize the power of the biomedical concepts and later the analysis concepts, which will really enable the translation of the protocol information into data collection, storage, analysis elements, all of which are needed for the CSR. And we'll discuss more on using biomedical concepts in a minute. But after you're done collecting the study details centered around endpoints and study epochs, the schedule of activities can be auto-generated. In fact, following the common protocol template, the entire data-related sections can be auto-generated. And this in of itself is quite helpful, because how many times have we found inconsistency issues in different protocol sections when developing the eCRF, which always calls back maybe a protocol amendment before you even really get going. When the centralized and digitized study details are used throughout the study, consistency gains from the reuse of the study details within the protocol also provide continuity between all major deliverables created in later steps, such as EDC specifications, STM, the SAP, and the CSR. Now, let's take a closer look at biomedical concepts. The information collected in the protocol builder should be captured as a biomedical concept metadata, which is basically a logical unit of knowledge, which would then be passed downstream and used to support later tasks. The biomedical concepts and analysis metadata would be the backbone that tied the objectives and endpoints to the schedule of activities, STM, SAP, and TLS. I'm sure many of you are familiar with biomedical concepts, but since they are so important, let me take a moment to provide an example. In the previous example Nick gave, we associated hypertension with the biomedical concept group of vitals, and through vitals to the biomedical concepts of the systolic and diastolic blood pressure. Those root biomedical concepts are associated with their own specific collection requirements that define how it will be collected in EDC and how it will be stored in STM. In this example, the graph illustrates the eCRF fields needed to collect and identify the systolic blood pressure with all its details, whether you should be sitting or however you're going to take your blood pressure. It is this level of detail that provides the linkage benefits that are required to feed the needs downstream. Let's spend a few minutes discussing the data collection by reviewing our second use case, the CRF builder. The goal of the CRF builder is to assist in the EDC setup by using the study design details to ensure 100% consistency with the protocol. The assistance is provided in 4 ways. The first is to allow the study team to see a CRF view of the forms before it actually goes into the EDC tool. So they're able to visually review how the protocol was interpreted and to provide a look at what the biomedical concepts are providing behind the scenes. The second is to provide the ability to view the forms fields at each visit to help the data managers, programmers, and even the statisticians better understand the structure of the incoming data. The third benefit is to produce detailed specifications that align with the study details, and if supported by the EDC tool, we can actually create a study design import file, and Nick had mentioned ODM and ALS, which will define the visit schedule, forms, and fields directly into the EDC tool, eliminating that step. And finally, at this point, you should be able to perform an impact analysis of between versions of the protocol or a previous snapshot during development. It is this impact analysis that would highlight a protocol amendment's changes to all downstream components. And as we have seen, some minor protocol updates could have major impacts on what the data is being collected and how it will be analyzed. For example, adding additional visits to an oncology study is a minor change in the protocol, but requires major changes in most EDC tools.
Yeah, and Bill, I really want to place an emphasis on that point, because we've done this analysis several times, and our most recent review that we performed, the average protocol has more than 3 amendments during a study's conduct. So we view the ability to perform an impact analysis as an essential requirement.
Yeah, I totally agree. And let's have another look at the biomedical concept graph now. As you can see on this graph, we have added additional red nodes to associate the protocol's endpoints and the required data right to their STTM storage location. And as you can imagine, using an analysis concept we mentioned earlier, this graph could be extended even further to include where that data will reside in your analysis database and the TLF details to complete the picture. But speaking of STTM, let's have a look at use case number 3, STTM conversion. The goal of the STTM conversion step is to create a CDIS standard database and associated documentation that can be used in a regulatory submission. Currently, the mapping of the input data is done manually by a programmer, or if you're fortunate, through some type of UI. The conversion should be done by having the machine learning algorithm utilize the study design data and the input metadata already available to decide which STTM path to take on the biomedical concept nodes. The input files could be from any current or future data source, including EDC, centrally collected data such as labs and ECGs, or even wearable devices or electronic health records, to name a few. The use of the biomedical concepts assists in both providing a consistent and proper database population and by providing documentation details needed for the defined XML and reviewer's guide documents. Currently, no matter how the data is being populated into STTM, the documentation is incomplete and inconsistent, which increases the level of effort in creating the submission documentation and also affects the quality of these documents. In fact, a recent review of defined XMLs highlighted the variations across companies and even within a company that are embedded in the defined XMLs. Once the data is truly stored in a standardized manner, the system should be able to auto-configure quality checks. These checks should be able to support anything from simple field range checks to complex cross-form checks, helping identify data outliers for the study team to investigate. Extending this with the use of analysis concepts, the TLFs can be generated and reviewed with the data that has been collected so far. Ideally, the TLFs could be automatically rerun against the data as new data is entered throughout the study conduct. And this will help identify how any of the data or its outliers are affecting the TLFs. As a point of reference, using our tool recently, we recently completed a conversion of input files to a fully compliant STTM database and documentation in only 2 hours. And if you compare that to a 4-week effort, you can appreciate the scale of improvement.
Yeah, that always gets me, Bill. That 2 hours over 4 weeks, I'll take the 2 hours every time.
Yeah, for sure. When we performed analysis to determine both the cost and the cycle time savings shared through the study, the design information across the various tools by the organization, we found over $500,000 of savings per study and over 10 weeks reduction from start of protocol to finalized CSR.
Yeah, so I think that's incredibly impactful when you talk about over $500,000 in savings, over the course of a study, 10 weeks reduction. And then when we factor in the point I was making before about your average protocol has 3 amendments, think of all the additional savings there when you can have that, automated impact analysis, and you're rapidly able to make adjustments based off those amendments and carry those through the metadata. So this is incredibly impactful, and there's really a compounding effect that you would see from this beyond that $500,000 in savings that we estimate. So thank you, Will, and thank you so much, everybody who spent the time to listen and show some interest in this topic. We've tried to provide you with a feel for how the study design information can be used to automate much of the downstream processes. Please feel free to reach out and connect with us to continue the dialogue. We are really looking forward to sharing more on these concepts if you're interested. Thank you and have a good rest of your day.